In the previous part, we outlined the historical and theoretical foundations of blackbody radiation. We examined the preliminary work of prominent physicists such as Gustav Kirchhoff, Joseph Stephan, Ludwig Boltzmann, and Wilhelm Wien. We also discussed how classical physics failed to explain the absorbed spectrum of blackbody radiation, namely the ultraviolet catastrophe predicted by the Rayleigh-Jeans law. In this part, we will explore Max Planck's revolutionary contributions to blackbody radiation, which marked the beginning of quantum mechanics. If you haven't seen the previous part, I highly recommend watching it, as it provides essential context for the developments we'll be discussing in this video. Before diving in, let's pay tribute to Max Planck by briefly summarizing his life. Max Carl Ernst Ludwig Planck was born in Kiel, Germany on April 23, 1858, and spent his early years there. When he was 9 years old, his family moved to Munich, where he became a pupil at the Maximilian Gymnasium, a grammar school. There, he received his first exposure to science from his mathematics teacher, Hermann Müller. Planck admired Müller's ability to visualize and explain the laws of physics with insightful examples. One explanation that particularly impressed him was Müller's explanation of the law of conservation of energy, the first law Planck recognized as having absolute, universal validity. At the age of 16, Planck enrolled at the University of Munich to study experimental physics and mathematics. He attended mathematics lectures by Gustav Bauer and Ludwig Seidel, as well as physics lectures by Philipp von Joly. When it came time to choose a field of study, Planck sought advice from von Joly, a prominent experimental physicist at the time. Von Joly advised him to avoid theoretical physics, believing the field was nearly complete following the discovery of the principles of thermodynamics. Later in life, Planck recalled, "As I began my university studies, I asked my venerable teacher, Philipp von Joly, for advice regarding the conditions and prospects of my chosen field of study. He described physics to me as a highly developed, nearly fully matured science, that through the crowning achievement of the discovery of the principle of conservation of energy, it will arguably soon take its final stable form. It may yet keep going in one corner or another, scrutinizing or putting in order a jot here and a tittle there, but the system as a whole is secured, and theoretical physics is noticeably approaching its completion to the same degree as geometry did centuries ago." That was the view 50 years ago of a respected physicist at the time. In 1877, Planck enrolled at the University of Berlin, where he studied for a year under the guidance of the physicists Gustav Kirchhoff and Hermann von Helmholtz, as well as the mathematician Karl Weierstrass. Despite the prominence of these scientists, Planck did not find their lectures particularly inspiring. Helmholtz rarely prepared his lectures properly. He would often make errors in his calculations at the blackboard, frequently pausing to search for data in his small notebook. It appeared that the lectures bored Helmholtz as much as they did his students, with only 3 remaining students attending his lectures, Planck being one of them. Kirchhoff, on the other hand, was the exact opposite. He would always deliver a carefully prepared lecture, with every word and every equation perfectly chosen. However, his lectures were so well prepared that they seemed to be memorized, which made them dry and monotonous. Under these circumstances, Planck decided to do his own reading on the subjects that interested him, particularly those related to the principle of energy conservation. It was not long before he discovered the writings of Rudolf Clausius, a German physicist and mathematician who formulated the structure of classical thermodynamics between 1850 and 1865. Planck admired Clausius' clarity of reasoning and his precise formulation of the 2 laws of thermodynamics. Clausius' influence led Planck to earn his doctorate in 1879 with a dissertation on the second law of thermodynamics, titled "About the Second Law of the Mechanical Theory of Heat." He completed the thesis in 3 months, concluding that all natural processes, without exception, proceed in the direction of increasing entropy. At the beginning of his thesis, he wrote, "The following considerations relate to all conceivable natural processes. not just the subject of heat. Unfortunately, Planck's thesis was not well received by the physicists of his time. None of his professors at the university fully understood its contents, as Planck realized through conversations with them. The dissertation was only accepted due to his strong reputation as a student. However, the most crushing feedback came from those closest to his thesis topic. Helmholtz likely never read it, and Kirchhoff harshly criticized it, believing that entropy could not be applied to irreversible processes. Planck wrote several letters to Clausius, but they went unanswered. He even attempted to visit him at his home in Bonn, only to find him away. Lastly, an exchange with Carl Newman yielded no productive results. Despite the lack of early recognition, Planck persisted in his study of entropy, publishing papers and gradually building his reputation as a physicist. In 1885, he was offered an associate professorship in theoretical physics at the University of Kiel, marking the beginning of his academic career. 4 years later, in 1889, Planck accepted the position of associate professor of theoretical physics at the University of Berlin, succeeding Kirchhoff after his passing, and by 1892 he had been promoted to full professor. During these years, Planck broadened his scientific knowledge and became acquainted with many prominent physicists, some of whom were leading figures in their respective fields. For Planck, the laws of thermodynamics were the absolute laws of nature. He was firmly convinced that the second law of thermodynamics was inviolable, dismissing any theories that suggested otherwise. One such theory was energetics, an outdated theory that views the world as composed of different forms of energy. At its core, the theory suggested that irreversibility was not essential and further denied the existence of absolute zero temperature. Planck was determined to challenge this theory and was soon joined by other physicists, including Ludwig Boltzmann. But Boltzmann's arguments were not exactly the same as Planck's. Boltzmann was one of the pioneers in the study of statistical mechanics, a theory that describes the behavior of systems with a large number of elements. One of his cornerstone discoveries was the eta theorem, which introduces a function eta for a given state of an ideal gas. The value of this function constantly decreases over time, and it is meant to represent entropy, from which one can deduce the second law of thermodynamics, the principle of increasing entropy. However, Boltzmann viewed the second law as a statistical law, a law of mere probabilities. He suggested that while it is extremely unlikely, it is not impossible for the entropy of a system to spontaneously decrease. In other words, the value of the eta function might increase at times. This implies that there are no truly irreversible processes in nature, only highly improbable ones, such as a broken glass spontaneously reassembling itself. This, of course, was a direct challenge to Planck's belief in the inviolability of the second law of thermodynamics. Furthermore, Boltzmann was a strong proponent of atomic theory, which posits that matter consists of a large number of identical particles, atoms or molecules, in constant random motion. Planck, however, was opposed to atomic theory and even hostile towards it, despite it being the foundation of Boltzmann's research. Interestingly, in 1882, Planck stated the following: "Despite the great success that the atomic theory has so far enjoyed, ultimately it will have to be abandoned in favor of the assumption of continuous matter." These conflicting views led to a strained relationship between Planck and Boltzmann. Boltzmann's harsh tone toward Planck continued to surface in his publications and personal conversations with him. It is only in the last years of his life, when Planck embraced atomic theory, that Boltzmann's attitude softened. Planck started actively searching for a theoretical foundation of the second law of thermodynamics, eventually turning his attention to Maxwell's electrodynamics in the hope of deriving irreversibility from it. It was not long before Planck discovered the work being done by physicists at the Imperial Physical Technical Institute on the blackbody radiation problem. It seemed a perfect choice for this purpose, as the problem was closely related to thermodynamics and electrodynamics. Reflecting on this in his autobiography, he wrote, "The measurements made by Lummer and Pringsheim in the German Physico-Technical Institute in connection with the study of the thermal spectrum directed my attention to Kirchhoff's law, which says that in an evacuated cavity bounded by totally reflecting walls and containing any arbitrary number of emitting and absorbing bodies, in time a state will be reached where all bodies have the same temperature, and the radiation in all its properties, including its spectral energy distribution, depends not on the nature of the bodies, but solely and exclusively on the temperature. Thus, this so-called normal spectral energy distribution represents something absolute, and since I had always regarded the search for the absolute as the loftiest goal of all scientific activity, I eagerly set to work. Before delving into the specifics of Planck's work on blackbody radiation, it is important to develop an elementary understanding of the concept of entropy. The first law of thermodynamics introduces a state variable called the internal energy of a system and states that it is a conserved quantity. There are two main ways of changing the internal energy of a system. First, by performing work on the system, or by allowing the system to perform work on its environment. And second, by allowing the system to exchange heat with its environment. The first law states that the change in the internal energy of a system is equal to the heat added to the system plus the work done on the system. Expressed mathematically, it is given by the following equation, where U is the internal energy of the system, Q is the heat added to the system, and W is the work done on the system. In the case of infinitesimal changes in the variables, the equation becomes this expression, where the different notations are used to emphasize the difference between the state variable U and the path variables Q and W. You may have heard an informal statement of the first law of thermodynamics that energy cannot be created or destroyed, only transformed from one form to another. While the first law of thermodynamics states that energy is conserved, it does not provide any information about the direction of spontaneous changes in a system. The second law of thermodynamics addresses this issue. It has many formulations, but the most common one, introduced by Clausius, states the following: no process is possible whose sole result is the transfer of heat from a colder to a hotter body. To quantify this statement, Clausius introduced a new state variable called the entropy of a system, which expresses the direction of spontaneous changes in a system. Entropy is defined by the following expression, where S is the entropy of the system, Q is the heat added to the system, and T is the temperature of the system. Entropy is often informally referred to as the measure of disorder in a system. The second law of thermodynamics can then be restated as follows. Any spontaneous process in any isolated system always results in an increase in the entropy of that system. Or, expressed mathematically, the change in entropy of a system is always greater than or equal to zero. As we shall see, entropy will play a central role in Planck's work on blackbody radiation. On March 21, 1895, Planck published his first paper on the emission and absorption of electromagnetic radiation. To model the interaction between matter and radiation, Planck imagined a simple harmonic oscillator, which he referred to as a resonator. He modeled his resonator after Heinrich Hertz's ideal model of the electric dipole oscillator. Planck embedded a large number of resonators in the walls of a cavity filled with radiation. These resonators would be excited by absorbing radiation incident upon them and would be damped by emitting radiation back into the cavity. The natural frequency of the resonators would closely match the frequency of the radiation in the cavity, hence the term resonator. Planck concluded that the radiation inside the cavity would evolve over time to a final stationary state, which, according to Kirchhoff's law, would inevitably result in the universal blackbody spectrum. Planck continued to study the interaction between the resonators and the radiation, leading to a series of 5 papers titled on irreversible radiation processes. He submitted them to the Prussian Academy of Sciences between February 1897 and March 1899. I will not present all the details of the papers, as they include extensive mathematical detail. However, the main result of Planck's work was the derivation of the fundamental equation for the spectral energy density of radiation given by this expression. It relates the spectral energy density of radiation of frequency nu to the average energy of a single resonator of natural frequency nu when the two are in thermal equilibrium with each other. In deriving this equation, Planck traded one problem for another. Instead of deriving the spectral energy density of the radiation, Planck now had to find the average energy of a single resonator. The key, Planck believed, was to determine the dependence of entropy of a resonator on its average energy. In his autobiography, he wrote, "It was an odd jest of fate that a circumstance which on former occasions I had found unpleasant, namely, the lack of interest of my colleagues in the direction taken by my investigations, now turned out to be an outright boon. While a host of outstanding physicists worked on the problem of spectral energy distribution, both from the experimental and theoretical aspect, every one of them directed his efforts solely toward exhibiting the dependence of the intensity of radiation on the temperature. On the other hand, I suspected that the fundamental connection lies in the dependence of entropy upon energy. As the significance of the concept of entropy had not yet come to be fully appreciated, nobody paid any attention to the method adopted by me, and I could work out my calculations completely at my leisure, with absolute thoroughness, without fear of interference or competition." In search of the definition of entropy, Planck turned to Boltzmann's eta theorem and determined the form that the entropy must satisfy, where f and g are arbitrary functions of the frequency nu. One of the requirements for the entropy was that this form had to be unique, which Planck asserted without any proof. After some considerations, Planck was able to determine the expressions of the arbitrary functions, and the entropy of a single resonator was given by this expression. By taking the derivative of the entropy with respect to the average energy, Planck obtained the following expression, which he equated to the reciprocal of the temperature of the resonator, following the definition of entropy. By isolating the logarithm and exponentiating both sides, Planck obtained the following expression. Isolating the average energy of the resonator, he found this expression. Finally, using his fundamental equation, Planck derived the spectral energy density of radiation as the following expression, which is the distribution law Wien obtained in 1896. By the time Planck published his last paper, the Wien distribution law had been confirmed through successful experimental tests. Taking the second derivative of the entropy with respect to the average energy, he obtained the following expression. Planck attached great importance to this second derivative, as it was the decisive factor for the irreversibility of the exchange of energy between the resonator and the radiation. He decided to denote the reciprocal of it with the symbol R. This meant that R depended linearly on the average energy of the resonator. Consequently, Planck believed he had achieved his goals. First, establishing irreversibility from electrodynamics, and second, deriving the universal law of blackbody radiation. From Paschen's measurements, Planck managed to obtain the values of constants A and B, where erg is the unit of energy in the centimeter-gram-second system of units. Planck summarized the results of irreversible radiation processes in an extensive paper submitted to Annalen der Physik on November 7, 1899. He claimed that the definition of the entropy he used, and therefore the radiation law, were a necessary consequence of the second law of thermodynamics. He argued, if, on the other hand, one tries to start from any distribution law different from the one given and computes from it in turn the entropy, then one arrives again and again at contradictions with the law of the increase of entropy. Interestingly, Planck recognized the significance of the constant B, subsequently identified as Planck's constant H, well before he uncovered its implications. It offers the possibility of establishing units for length, mass, time, and temperature, which are independent of specific bodies or materials and which necessarily maintain their meaning for all time and for all civilizations, even those which are extraterrestrial and non-human, constants which therefore can be called fundamental physical units of measurement. Planck established them using the constants A and B, the speed of light c, and the gravitational constant g. These correspond to the units of length, mass, time, and temperature, respectively. We now call these units the Planck units. The most glaring flaw in Planck's derivation of Wien's distribution law was the absence of proof for the uniqueness of the entropy function. Without establishing this uniqueness, his derivation remained incomplete. In the same year, 1899, Lummer and Pringsheim observed systematic deviations of Wien's distribution law at low frequencies. These findings led Lummer and Pringsheim to question the validity of Wien's distribution law. Regarding Planck's work, they stated, "It would be conclusive only in the presence of a proof that any form differing from that leads to an expression for entropy which violates the second law." To establish this proof, Planck imagined a system that starts in equilibrium and is then disturbed from it by adding a small amount of energy delta U to one of the resonators. The system then returns to equilibrium by itself with a transition described by the following equation, where du nu denotes the change in the energy of the resonator associated with a change in entropy ds. Delta U is the difference between the average resonator energy U nu and the equilibrium energy U naught. And sigma is the damping constant of the resonator. Planck now had to derive the expression for the change in the total entropy of the system, that is, the resonator and the cavity, in a time interval dt during the return of the system to equilibrium. He obtained the following expression, where the suffix 0 denotes the equilibrium state. Planck reasoned that du nu and delta U must have opposite signs. dt dst must be positive, and the equilibrium position must be a local maximum if this expression holds. Where f is an arbitrary function of the average energy of the resonator. To determine this function, Planck considered the displacement of a system of n many resonators from equilibrium. In such a system, the total displacement of the energy can be expressed as follows. Planck postulated that entropy is an additive quantity, which means that the change in the total entropy of the system is given by the following expression. From these considerations, Planck obtained the following expression, from which he obtained this simple relation. This equation is satisfied only when f is proportional to the reciprocal of the average energy of the resonator. Therefore, the reciprocal of the second derivative for the entropy with respect to the average energy of the resonator is given by the following expression, where alpha is a constant depending on the frequency of the resonator. Recalling the expression Planck derived earlier for R, it follows that the constant alpha is given by the following expression, and R takes the form Planck found earlier. For Planck, this result was the final proof of the uniqueness of the entropy function. He commented the following in the paper he published in Annalen der Physik on March 22, 1900. Since this computation yields the same expression for entropy as before, my view of the formula's significance is still further strengthened, even though its basis has been in part somewhat displaced. However, Planck's success was short-lived. We're now at the point where we left off in the first part. The experimental data obtained by the physicists Rubens and Kohlbaum in 1900 revealed a complete and undeniable failure of the Wien distribution law at low frequencies. Furthermore, Planck's colleagues pointed out a serious flaw in his proof of the uniqueness of the entropy function. There is not just one, but an infinite number of possible choices for the entropy function. These events dealt a severe blow to Planck's work. Rubens and Kohlbaum intended to present their results in a paper to the German Physical Society. To their dismay, the next meeting was scheduled for October 5, 1900, and they had little to no time to prepare it. They decided to wait until the following meeting 2 weeks later. Meanwhile, Rubens, who was a close friend of Planck, knew he would be keen to hear about their discoveries. Rubens, together with his wife, visited Planck's residence in the Berlin suburb of Grunewald on October 7, 1900, to deliver the news. Upon learning of Rubens' findings, Planck realized that his previous work, which relied on Wien's distribution law, was now at risk. After Rubens left, Planck immediately began to consider the implications of Rubens' findings. Planck summarized his observations the following way. Thus, direct experiments established two simple limits for the function R. For small energies, R is proportional to the energy. For larger energy values, R is proportional to the square of the energy. Obviously, just as every principle of spectral energy distribution yields a certain value for R, so also every formula for R leads to a definite law of the distribution of energy. The problem was to find such a formula for R which would result in the law of the distribution of energy established by measurement. Therefore, the most obvious step for the general case was to make the values of R equal to the sum of a term proportional to the first power of the energy and another term proportional to the second power of the energy, so that the first term becomes decisive for small values of the energy and the second term for large values. It follows from Planck's argument that in the low frequency limit, R must satisfy the following equation, where beta is a constant depending on the frequency, and in the high frequency limit, where Wien's distribution law is valid, R must satisfy the equation he derived earlier. Where alpha was now taken to be a pure constant. By pure intuition, Planck interpolated these two equations to derive the following equation for the equilibrium entropy, which is valid for all frequencies. Planck then integrated the reciprocal of this equation and found the following expression, which he equated to the reciprocal of the absolute temperature from the definition of entropy. Upon isolating the logarithm and exponentiating both sides, he obtained this expression. Finally, after isolating the average energy of the resonator, he found this equation. When beta is much greater than the product of alpha and temperature T, this equation reduces to the expression Planck derived earlier. It follows that beta is equal to the product of B and nu, and A is equal to the ratio of B to alpha. Using his fundamental equation, Planck derived the spectral energy density of radiation as the following expression. Planck later changed the symbols alpha and B to K and H, respectively, and the formula became the following expression. This is the famous Planck radiation law in its final modern form. Planck's student, Hettner, later recalled, the same evening he reported his formula to Rubens on a postcard, which the latter received the following morning. 1 or 2 days later, Rubens again went to Planck and was able to bring him the news that the new formula agreed perfectly with his observations. On October 19, 1900, at the meeting of the German Physical Society, Kohlbaum demonstrated the experimental results he had obtained with Rubens. Following the lively discussion of Kohlbaum's presentation, Planck presented his new formula, describing it as an improvement of Wien's equation for the spectrum. He declared, the interesting results of long wavelength spectral energy measurements, which were communicated by Mr. Korlbaum at today's meeting, and which were obtained by him and Mr. Rubens, confirmed the statement by Mr. Loomer and Mr. Brinksheim, which was based on their observations that Wien's energy distribution law is not as generally valid as many have supposed up to now, but that this law at most has the character of a limiting case, the simple form of which was due only to a restriction to short wavelengths and low temperatures. Since I myself, even in this society, have expressed the opinion that Wien's law must be necessarily true, I may perhaps be permitted to explain briefly the relationship between the electromagnetic radiation theory developed by me and the experimental data. Planck's radiation law was tested many times in the following years, performing perfectly at all temperatures and frequencies. It was soon universally accepted as the solution for the spectral energy distribution of blackbody radiation, which is valid still today. For Planck, however, this was not the end of the story, as he described his work as a mere lucky intuition. He now had to provide a theoretical foundation and physical motivation for his interpolation formula. Despite his long-standing opposition to Boltzmann's ideas, Planck had to abandon his thermodynamic approach and adopt Boltzmann's probabilistic conception of entropy to establish a theoretical foundation for his interpolation formula. He turned to Boltzmann's 1877 seminal paper titled On the Relationship Between the Second Fundamental Theorem of the Mechanical Theory of Heat and Probability Calculations Regarding the Conditions for Thermal Equilibrium. Later, in his Nobel Prize lecture, Planck recalled, "I busied myself from then on, that is, from the day of its establishment, with the task of elucidating a true physical character for the formula, and this problem led me automatically to a consideration of the connection between entropy and probability, that is, Boltzmann's trends of ideas, until after some weeks of the most strenuous work of my life, light came into the darkness, and a new undreamt of perspective opened up before me." Planck started his second derivation with the following assumptions. Let us consider a large number of monochromatically vibrating resonators, n of frequency nu per second, n prime of frequency nu prime, and double prime of frequency nu double prime, with all n large numbers, which are at large distances apart and are enclosed in a diathermic medium with light velocity c and bounded by reflecting walls. Let the system contain a certain amount of energy, the total energy ET, erg, which is present partly in the medium as traveling radiation and partly in the resonators as vibrational energy. The question is how in a stationary state this energy is distributed over the vibrations of the resonators and over the various colors of the radiation present in the medium, and what will be the temperature of the total system. In his paper, Boltzmann introduced the statistical interpretation of entropy within the kinetic theory of gases, defining it as a measure of the number of possible microscopic configurations corresponding to a macroscopic state of a system. He concluded that it is proportional to the natural logarithm of the number of possible microstates p corresponding to a macrostate of the system. This relation is expressed as the following equation, where S is the entropy of the system and p is the number of possible microstates. Planck realized that these constants A and H have units of degrees Celsius seconds and erg seconds, respectively, and could be related to each other by another constant that had the units of degrees Celsius per erg or erg per degrees Celsius, the units of entropy. He assigned it the symbol K after the German word Konstante and defined it as the expression we have seen earlier. Planck chose it as the constant of proportionality between the entropy and the natural logarithm of the number of possible microstates, and he expressed the entropy as the following equation, where the constant K is now known as the Boltzmann constant, often denoted as Kb. Boltzmann never introduced this constant, and Planck later remarked that this was a peculiar state of affairs, which can be explained by the fact that Boltzmann, as appears from his occasional utterances, never gave thought to the possibility of carrying out an exact measurement of the constant. Planck further reformulated this equation by substituting P with W, where W represents probability. It is interesting to note that this equation, rather than Boltzmann's original equation, is now engraved on Boltzmann's tombstone in Vienna. Employing his new definition of entropy, Planck set the total entropy of the n-resonator system to within an arbitrary additive constant as the following expression, where Sn is given by the product of n and the entropy of a single resonator. Next, Planck considered to assign to each group of resonators of a given frequency a given arbitrary definite energy, an energy E to the n, E prime to the n prime, E double prime to the n double prime, and so on. The sum of those energies is given by this expression, where E res is the total energy of the resonators. The total energy of the system is the sum of the energy of the resonators and the energy of the radiation, which is given by this expression. Now, Planck had to distribute the energies over the separate resonators of each group, starting with the distribution of E over the n resonators. If E is considered to be a continuously divisible quantity, this distribution is possible in infinitely many ways, and the probability W of the n resonator system would diverge to infinity. Planck then reasoned, we consider, however, this is the most essential point of the whole calculation, E to be composed of a very definite number of equal parts, and use thereto the constant of nature h. This constant, multiplied by the common frequency nu of the resonators, gives us the energy element epsilon in erg, and dividing E by epsilon, we get the number p of energy elements, which must be divided over the n resonators. This meant that E can take on only certain discrete values, such as 0, epsilon, 2 epsilon, 3 epsilon, and so on, where the total number of energy elements P is given by the ratio of the total energy E to the energy element epsilon. Next, Planck had to find the number of ways the P energy elements can be partitioned over the n resonators. Each individual partition is called a complexion, following the ideas of Boltzmann. Planck found the possible number of complexions as this expression. To understand how Planck arrived at this expression, we will consider an example from which we can generalize the result. Let's say we have 7 energy elements, that is P equals 7, and 5 resonators, that is N equals 5. The system would look like this. Now, it is not immediately clear how we should partition the 7 energy elements among the 5 resonators. To simplify the problem, we may refer to the method used by Paul Ehrenfest and Heike Kamerlin-Onnes in their 1814 paper titled Simplified Deduction of the Formula from the Theory of Combinations, which Planck uses as the basis of his radiation theory. Following their method, we may put separators between successive resonators. The system would look like this. Therefore, the space between 2 consecutive separators, as well as the space to the left and right of the first and last separators, corresponds to a single resonator. Placing energy elements in the space between 2 separators, or to the left or right of the first and last separators, is equivalent to partitioning the energy elements into resonators. The number of separators is 1 less the number of resonators, so we have n-1 separators. Now, let's determine how many ways we can partition 7 energy elements into 5 resonators. This is a valid arrangement. This is also a valid arrangement. And this is a valid arrangement. The separators can also be rearranged. Therefore, in general, we have p plus n minus 1 elements that can be arranged in different ways. The total number of arrangements is then simply factorial of p plus n minus 1. However, you have probably noticed that certain arrangements are not distinct. For if I were to switch the positions of these 2 energy elements, or these 2 energy elements, the system would remain the same. This is because the energy elements are indistinguishable It certainly would not be the case if the energy elements were distinguishable, and you would have noticed the difference. Therefore, we must exclude identical arrangements from the total number of complexions. To do so, we simply divide the total number of arrangements by the number of arrangements of the p energy elements, which is the factorial of p. The separators are also indistinguishable, as they correspond to the indistinguishable resonators, so we must divide also by factorial of n-1 to account for this. We derived Planck's expression for the number of complexions. Planck now put forward a hypothesis that the probability W of n resonators having a total energy E is proportional to the number of complexions Z. Using this hypothesis, Planck set the entropy of the n resonator system as this expression. Substituting the expression for the number of complexions, we have this expression for the entropy of the system, which we can approximate the following way. Let's rewrite it as follows. We can further simplify our result using Stirling's approximation, which can be used for large values of the argument of the logarithm. So we have this expression for the entropy of the n resonator system. Taking n as a common factor and multiplying and dividing by n the argument of the logarithm, we obtain this expression. Recalling the relation for the number of energy elements given by this expression, we can substitute it into the expression for the entropy of the system. Upon closer inspection, we can see that the following expression corresponds to the average energy of a single resonator, U nu. Therefore, we can rewrite the entropy of the n resonator system as this expression. Finally, from the expression for the entropy of the system, we can write the entropy of a single resonator as this expression. Planck now was able to determine the average energy of a single resonator. Taking the derivative of the entropy with respect to the average energy of the resonator, we obtain this expression, which is equal to the reciprocal of the temperature. We can further simplify our expression as follows. Exponentiating both sides, we obtain this expression. Isolating the average energy of the resonator, we finally obtain it as this expression. Recalling the first derivation of Planck's radiation law, we can identify the energy element epsilon as the product of the frequency nu and the constant h. Therefore, the energy of a resonator is equal to this expression. And the energy density of radiation in the cavity is equal to this expression, which is the same equation Planck obtained in his first derivation. The theoretical foundation of the Planck radiation law, therefore, was established. Planck presented his results at the meeting of the German Physical Society on December 14, 1900, on a Friday evening at 5 p.m. with a lecture titled On the Theory of the Energy Distribution Law of the Normal Spectrum. Unknown to the audience and to Planck himself, this same day would be considered by many as the birth of quantum theory. He later published a paper to Annalen der Physik on January 7, 1901, that summarized his work. The pivotal idea of Planck's second derivation was the idea of introducing discrete energy elements, epsilon. This concept is rooted in Boltzmann's work, where he employed it as a mathematical tool to simplify his calculations when counting the number of possible microstates of a gas of molecules. Boltzmann then seamlessly returned to the classical continuum of energy by taking the limit epsilon to 0. Planck followed Boltzmann's approach by assigning integral multiples of these discrete energy elements to his oscillators of frequency nu. However, he departed fundamentally by fixing epsilon to a finite value, where the proportionality constant h is a new universal constant called Planck's constant, instead of letting epsilon become vanishingly small as required by classical physics. Planck did not take this latter step because he could not. Doing so would have led to the Rayleigh-Jeans law, which is known to be incorrect. This meant that his oscillators could emit and absorb radiation only in discrete amounts of energy, the product of h and nu, where nu is their natural frequency that matches that of the radiation. In a letter to an American physicist, Robert Williams Wood, dated October 7, 1931, Planck wrote the following: "My dear colleague, you recently expressed the wish, after our fine dinner in Trinity Hall, that I should describe, from a psychological viewpoint, the considerations which had led me to propose the hypothesis of energy quanta. I shall attempt herewith to respond to your wish. Briefly summarized, what I did can be described as simply an act of desperation. By nature, I am peacefully inclined and reject all doubtful adventures. But by then I had been wrestling unsuccessfully for 6 years, since 1894, with the problem of equilibrium between radiation and matter, and I knew that this problem was of fundamental importance to physics. I also knew the formula that expresses the energy distribution in normal spectra. A theoretical interpretation therefore had to be found at any cost, no matter how high. It was clear to me that classical physics could offer no solution to this problem and would have meant that all energy would eventually transfer from matter into radiation. In order to prevent this, a new constant is required to assure that energy does not disintegrate, but the only way to recognize how this can be done is to start from a definite point of view. This approach was opened to me by maintaining the two laws of thermodynamics. The two laws, it seems to me, must be upheld under all circumstances. For the rest, I was ready to sacrifice every one of my previous convictions about physical laws. Boltzmann had explained how thermodynamic equilibrium is established by means of a statistical equilibrium, and if such an approach is applied to the equilibrium between matter and radiation, one finds that the continuous loss of energy into radiation can be prevented by assuming that energy is forced at the outset to remain together in certain quanta. This was purely a formal assumption, and I really did not give it much thought, except that no matter what the cost, I must bring about a positive result. From the validity of Planck's radiation law, we can derive the approximations of Wien's distribution law, which is valid in the limit of high frequencies and low temperatures, and the Rayleigh-Jeans law, which is valid in the limit of low frequencies and high temperatures. In the first case, the product of h and frequency nu is much larger than the product of k and temperature T, and so the exponential dominates in the denominator. Therefore, the spectral energy density of the radiation in the cavity becomes this expression, which is precisely Wien's distribution law. In the second case, the product of h and frequency nu is much less than the product of k and temperature T. If we expand the exponential in the denominator as a Taylor series, we obtain this expression, where all the terms above the first degree can be neglected. Therefore, the denominator becomes this expression. And the spectral energy density of the radiation in the cavity becomes this expression, which is the Rayleigh-Jeans law we saw earlier. Therefore, Planck's radiation law is able to reproduce Wien's distribution law for high frequencies and low temperatures, the Rayleigh-Jeans law for low frequencies and high temperatures, and also bridge the gap between the two laws. Integrating Planck's radiation law over all frequencies, we should also obtain the Stefan-Boltzmann law, which gives the total energy density of the radiation in the cavity. This allows to determine the radiation constant and the Stefan-Boltzmann constant correctly. From the experimental data, Planck managed to determine the values of the constants h and k. The numerical values of h and k, which I mentioned, were calculated from that equation using the measurements by Korlbaum and by Lummer and Pringsheim. Expressed in SI units, the values of the constants are as follows. These values are very close to the modern accepted ones. As an important side note, if we were to compare the values of the constant b determined by Planck from Paschen's experimental data in 1899 with the value of the constant h we just saw, we would find that they are not quite the same. Despite this discrepancy, Planck believed that the constants p and h were equivalent, and attributed the discrepancy to experimental uncertainties. The variation in the figures corresponds to the deviations in the measurements of the various observers and provides an approximate idea of the uncertainty still prevailing at the time. However, the constants are not equivalent. Furthermore, it follows that the Boltzmann constant k, which Planck defined as the ratio of the constants h and a, is also incorrect. I will not delve into the details of these mistakes as they are beyond the scope of this video. For a more detailed discussion of this topic, those who are interested can refer to Hans Kangros' book titled Early History of Planck's Radiation Law, pages 144-147. On November 6, 1947, the weekly magazine The Listener printed a talk given by Edward Andrade, an English physicist, in which he paid tribute to Planck's work and said the following words: "If I hesitate to put Planck on a level with Newton and Einstein, it must be partly on the ground that he did not seem to know quite what he had done. Planck seems to have been reluctant to realize the range of his innovation." Afterwards, Andrade received a letter from Planck's widowed wife in which she wrote the following: "You have done justice to the scientist and to the man in every respect. I should only like to make one small exception. You think that he did not realize the scope of his discovery, yet he did do so, though, of course, not in all its consequences. He said to our son, with whom he had gone through a book on Galileo, Newton, and Kepler, 'Look, my boy, I shall one day be in a book like this.'" One of Planck's favorite leisure activities was walking in the Grunewald forest, where he would often take his other son, Erwin. One early morning, during one of these walks, Planck reportedly told his 7-year-old son the following, presumably before the December meeting of the German Physical Society: "Today I have made a discovery as important as that of Newton." Did Planck fully grasp the profound significance of his discovery, or was he simply trying to convey to his young son the importance of his new radiation law? In truth, it was neither. What Planck was genuinely excited about was his discovery of not one, but two new fundamental constants of nature: the quantum of action, h, and the Boltzmann constant, k. Planck, in a groundbreaking insight, unveiled an underlying structure of the emission and absorption of radiation, namely, that energy can be emitted and absorbed only in discrete amounts. However, he failed to grasp the more significant and fundamental idea that energy itself is quantized, that it is not a smooth, continuous entity, but instead exists in indivisible, separate units, or quanta. This realization eluded Planck for many years, hidden within the dense undergrowth of his notes and papers, unarticulated in his speeches and lectures. The scientific world, oblivious to the treasure buried in plain sight, also failed to grasp its significance. It would take a true genius to see what everyone else could not. And so, fate intervened, selecting an unlikely visionary, a humble patent office clerk, working in the quiet anonymity of Bern, Switzerland. In this ordinary setting, nature revealed its laws to him, igniting the spark of a scientific revolution that would forever change the course of human history.
Nun möchte ich aber noch zum Schluss ein Wort sagen, was mein Gewissen erleichtern soll. Ich habe hier auf eine freundliche Einladung hin heute das ist ja wohl der 15. Dezember 1942, hier in Berlin, in der Jägerstraße 26, einige Worte gesprochen in das Filmarchiv, damit spätere Geschlechter mal, wenn Sie Interesse daran haben, von meiner Persönlichkeit Notiz nehmen können. Aber ich möchte hier hervorheben, dass Sie das, was Sie hier von mir hören und sehen, nicht als sozusagen als endgültige Abbildung meiner Persönlichkeit ansehen wollen. Denn was ich hier gesagt habe, das ist aus dem Stegreif entstanden, wie mir gerade eingefallen ist. Vorbereiten habe ich mich nicht in der Weise können, wie ich wohl sonst getan hätte, wenn ich gewusst hätte, wie ich hier auftreten soll. Also ich bitte dies nur als einen Versuch zu nehmen, mich zu äußern, damit überhaupt etwas von mir überbleibt. Wer sich genau über meine Persönlichkeit orientieren will, den bitte ich, sich an das zu halten, was ich geschrieben und was ich gedruckt habe. Für das kann ich einstehen. Je älter man wird, umso mehr fühlt man die Verantwortung für das, was man spricht. Und deshalb bin ich in den letzten Jahren gewohnt, was ich von mir gebe, alles vorher genau zu überlegen und mich vorzubereiten für jeden Schritt, den ich tue. Das ist heute nicht geschehen. Und infolgedessen muss ich also ein Fragezeichen machen hinter dem, was ich hier gesagt habe, und bitte das wohlwollend zu beurteilen.